Good morning, students. Today we'll discuss about a very important topic of electrostatic, that is Gauss theorem or a Gauss law. Before starting this law, we should first understand the concept of area vector. Now, what exactly is area vector? Suppose this is a surface element of any body, and over this surface there is a small element ds. Then the area vector is represented by ds is equal to ds n cap. That means the magnitude of this area vector is ds and the direction is normal to the surface. This concept is very much important and essential to discuss Gauss law. Second important concept is electric flux. Electric flux is the measure of total number of electric lines of force passing normally through that area. Now consider a surface S, which is shown over here. There is a small element ds over the surface. These are the electric field lines which are passing over the surface, represented by E. The direction of the area vector, as I have told you, is normal to the surface. So this is a normal which has been drawn on the surface S. So ds vector is equal to ds n cap, and the direction of electric field is shown over here, and the angle between the electric field direction and the area vector is theta. So electric flux over this small element ds is defined by d phi is equal to E dot ds. Now opening the dot product, it is E ds cos theta, where theta is the angle between electric field and ds, which is a area vector. Now this electric flux is a small quantity, is a small value d phi, and it is a scalar quantity excuse me, whose unit is Newton meter square per coulomb. After defining the area vector and the electric flux, now we can proceed for the Gauss theorem. Now Gauss law or a Gauss theorem, it states that total electric flux through a closed surface is 1 upon epsilon naught times the net charge enclosed by that closed surface. Let's try to prove it and try to understand what exactly Gauss law states. Now consider at point O there is a small positive charge plus Q, and suppose my aim is that I have to find the electric field at point P, which is at a distance r from here. Now in order to apply a Gauss law, first essential condition is that the surface need to be closed. That means now we have to enclose this particular charge. So we draw a surface which is enclosing this particular charge. This surface is called as a Gaussian surface. Since this is a point charge, so it will be an hollow sphere. The shape of the Gaussian surface will be a hollow sphere. Now suppose that Gaussian surface is represented by S. Now consider a small element ds at the point P, where we have to evaluate the electric field. Now we draw the area vector since it is normal to the surface. So this is the direction of the area vector, ds vector, and the direction of the electric field. Now in order to find the direction of electric field over a point P, we place a test charge which is positive in nature. Now positive is going to repel. So the direction of the electric field and the direction of the area vector, both are in same direction. That means the angle between them is 0. Now let's try to prove Gauss theorem. So electric field at point P, which is at a distance r, is given by 1 upon 4 pi epsilon naught q upon r square. Now by the definition of electric flux, small elemental flux is equal to E dot ds. Since the angle between electric field and ds is 0, so I put cos 0 over here. So d phi comes out to be equal to, I substitute the value of E, that is 1 upon 4 pi epsilon naught q upon r square ds, and cos 0 is 1. So if I have to evaluate the total electric flux, I have to integrate this small electric flux. So when I integrate, 1 upon 4 pi epsilon naught q upon r square comes out of the integration, and this is a closed integration over a surface S ds. The closed integration over this complete surface will be equal to the surface area of this sphere, and the surface area of this sphere will be 4 pi r square. So 4 pi cancels with 4 pi, r square cancels with r square, so the total flux comes out to be equal to q upon epsilon naught. This proves Gauss theorem, and the total electric flux over a closed surface is now 1 upon epsilon naught times the charge enclosed by this particular surface. After giving the proof of the Gauss law, our next aim will be that we will be trying to find the various applications of the Gauss law. Now there are numerous applications of the Gauss law. We will be discussing it one by one. Suppose we start with first application, that is electric field due to infinitely long charged wire with a given linear charge density of lambda. Just to give you a recall, that linear charge density lambda was called as charge per unit length. So this is a charged wire on which a positive charge, which is carrying a positive charge, and suppose my aim is to find the electric field at point P, which is at a distance r. So first important step, as I have told you, in order to apply a Gauss law, we have to first enclose this particular surface, and the geometry that comes out after enclosing this wire which is carrying a positive charge is a cylinder. This is a finite length cylinder of length L, okay, and the radius r. So we put a small element ds over here. The direction of the area vector is normal to the surface, and the direction of the electric field can also be calculated by placing a test charge. So the direction of electric field and the area vector is same as far as point P is concerned. Now we divide this entire surface into three surfaces. We mark S1, S2 and S3. And when we are calculating the total electric flux due to this complete cylinder, then total electric flux will be E dot ds over this complete surface S, which is the combination of the surface S1, S2 and S3. So since flux is a scalar quantity, so E dot ds1 first we will calculate for the surface S1, then we will add it to E dot ds2 for the surface S2, and then E dot ds for the surface S3. Now we will study it one by one. Let's consider the case for the first case when we are talking about the surface S1. So for the surface S1, if we see, E and ds are in same direction, so the angle between them is 0. So it becomes E integration of ds1. If I am talking of the second surface, that is S2, in this particular case the direction of the ds is normal to the surface and the direction of the electric field is perpendicular. So electric field is in this direction, ds is in this direction, so the angle between them is 90 degrees. Same thing happened with S3. For S3, if I talk of, ds3 is normal to the surface, electric field is perpendicular to ds3, so again the angle between them will also be 90. Hence the contribution of the flux due to S2 and S3 becomes 0. So the total flux becomes E integration ds1. So if I am talking of S1, now here integration of ds1 will be the curved surface area of the cylinder, which is 2 pi r into length L. Okay. Now according to Gauss law, the total flux is Q upon epsilon naught. Now as we know that Q is equal to lambda into L, as I have told you that lambda is the linear charge density. So I substitute in place of flux E into 2 pi RL, which I have calculated over here, and Q is equal to lambda into L upon epsilon naught. So L cancels with L and lambda become upon epsilon naught is equal to E into 2 pi r, or E is equal to lambda upon 2 pi epsilon naught r. So this is the first application of a Gauss law. Thank you very much.